So to begin, energy is for a skeletal muscle is needed for two primary things. For first, myosin ATPase activity, and that consists of about 70% of the energy needs. And then secondly, with a calcium pump to actively return calcium back into the sarcoplasmic reticulum. And so that takes about 30% of the muscle energy. Okay, so at rest and for mild exercise, where muscles get their energy from is from fatty acids from aerobic respiration. With moderate intensity exercise, we're looking at glycogen stores to get energy. And then lastly, for heavy exercise, we get energy from blood glucose levels, blood glucose. And as the intensity of exercise actually increases, then we have more channels that are inserted in the sarcolemma. And so that's going to pump more glucose into the cell so that we have that energy. So there's two different things I want to talk about. First is maximum oxygen uptake. Most of you probably have heard of this as VO2 max, but also has the name of aerobic capacity. So this is when it tells us if a person is undergoing light, moderate, or heavy exercise, and it's determined by several things. So person's age, sex, size, and athletic training. Typically, individuals that have low athletic training, that don't exercise nearly as much, are going to have a lower VO2 max, and those that have, like say, marathon runners, they'll have very high VO2 max. And typically we see this being higher in males than in females, and then also younger people will peak up about between 25 to 30, and then it steadily starts to decrease after that. And so the ranges for normal considerations are for 12 milliliters of oxygen per minute per kilogram of body weight. And then on the high range would be 84 milliliters of oxygen per minute per kilogram of body weight. And so this is important because this helps to tell us with like anaerobic respiration, anaerobic exercises, we use this for the first 45 seconds to 90 seconds when we're undergoing moderate to heavy exercises. And so this is going to help increase then oxygen supply. Now, lactate threshold is also important because this is also known as anaerobic threshold, and it helps to determine exercise intensity for a person. It's a little bit different than VO2 max because it tells us the percentage of maximum oxygen uptake when it increases in blood lactate levels. So this typically starts peaking at about 50 to 70% of VO2 max. The oxygen debt that occurs is when an individual exercises, the oxygen is actually coming from reserves in hemoglobin found on the erythrocytes and myoglobin found specifically within muscle, okay? And this helps to create the cross bridges in muscle contraction, and it helps to actively pump that calcium back to the sarcoplasmic reticulum at rest. So here, this is a great energy need as well. And the purpose of the oxygen then is help to metabolize the lactic acid, because otherwise we'll have an increase in hydrogen ions that are produced, and so that's what helps to give that acidic burn to our muscles. So with oxygen debt too, and in response to exercise, we have our breathing rate is going to increase, and it helps to repay this debt so that we have a continuous supply of oxygen for our hemoglobin and myoglobin. With continued exercise, what happens is that ATP is used faster than it can be created through cellular respiration. So what we have then is ADP is going to combine with inorganic phosphate from phosphocreatinine, okay? So then the creatinine is going to be produced by the liver and kidneys, or will be obtained through our diet. And then what we have then are these phosphocreatinine stores, and so that's going to then produce this extra ATP that we need when we're undergoing exercise. So creatinine supplements, which are found over the counter, can actually increase muscle phosphocreatinine levels so for storage of ATP, it helps with the short-term high-intensity exercises when we really need it. But if it's used long-term, there have been found causes with liver damage as well. However, in the short term, so we do have, again, intrinsic levels of this phosphocreatinine, and then which is going to help store those ATP molecules. So I'm sure you've heard about the different types of fibers that we have within our muscles. So the first that we'll cover, slow twitch fibers. These are also known as type 1 fibers. These tend to be for longer duration type exercises or even for maintenance of like posture. And so they have a slower contraction speed. They can undergo contractions for longer periods without fatigue, and sometimes some muscles can go indefinitely actually. These are going to be more red in color because they have a rich capillary supply. They have a lot more mitochondria to them, helping with that red color as well. And then more respiratory enzymes to help with oxygen and that oxygen debt. So that helps to replenish it, and then also has more myoglobin, which is specific to skeletal muscle. And so these are considered to be slow oxidative fibers because they tend to have a high oxidative capacity. And then these are found a lot in our, again, postural muscles. A good one example is our soleus muscle, which is directly beneath our gastrocnemius. And so 96% of that muscle is actually type 1 slow twitch fibers, and so has a very deep red color to it. And so here in this figure, what we're looking at, so here would be like somebody who's a long distance runner, and so you see these red fibers represents a lot more of them than, say, those fast twitch fibers. So the other types that we have are the fast twitch and the intermediate fibers. So the fast type are also known as the type 2X fibers, and so these are with fast contraction speeds. These are going to fatigue a lot faster, and so we can only use them for short durations. They have less capillaries, hence they have this white appearance to them. They have less mitochondria as well, and less respiratory enzymes and less myoglobin. All right, so that's why we are not able to use these for long durations as we are with the slow twitch fibers. However, though, they do have more glycogen stores, and so these are often called the glycolytic fibers as well. And so we find these within our stronger muscles when we need like rapid bouts of bursts of speed. And so actually, a good example of a muscle that is predominantly fast type is going to be our extensor hallucis longus, our big toe muscle. That is like 98% of this type 2X fiber. The last type that we have is the intermediate, and so this is considered as type 2A, and it falls actually under the fast twitch fiber. And it has, though, a higher oxidative capacity, and so this is known as the fast oxidative fiber. How it's going to fall in between the slow and type 2X fibers in terms of the number of capillaries, mitochondria, and then respiratory enzymes as well as myoglobin. All right, so just in this figure, what we have here, so this would be an example of using more of the type 2X. So here this person has a lot more of the white fibers. And so, like, for example, this would be our extensor hallucis longus. Most of our muscles are going to fall under the intermediate category in terms of fiber distribution. However, people are going to vary greatly in the percentage of fast and slow twitch fibers in their muscles, and a lot of it is due to genetics as well as due to training. And so this table gives a great representation of the differences between the three different types of fibers. So here we have that slow oxidative type 1 fiber. Here is the fast oxidative type 2A fiber, and then the fast glycolytic white type 2X fiber. All right, so difference between these three, if you look at here, let's look at the intermediate fiber first. You'll find that everything is intermediate in terms of like diameter of the muscle, Z-line thickness of the sarcomere, glycogen content, as well as resistance to fatigue. Whereas like with the slow oxidative fiber, these tend to be smaller. They're going to have wider Z-line thicknesses within that sarcomere. Again, helps to maintain those long durations, such as like with posture. And then the glycogen content is going to be lower, but then high resistance to fatigue. When you compare that to the fast glycolytic 2X, then we'll have low resistance to fatigue, so burn out faster. Glycogen content is going to be higher, but then a narrower range for that Z-line thickness. Okay. So just to give you an idea about abundance of fiber, so if we look at your average couch potato, here this individual is going to have about 40% of the slow type fiber, then we'll have about 30% of the fast type 2X, and then another 35% of that intermediate fiber. However, let's look at an extreme endurance athlete here. So a lot more of the type 1 slow type, but then look here, we're having fewer of that fast type 2 fiber. World-class marathon runner, so similar here. Lack of those intermediate fibers is what we're seeing. However, a higher percentage of the fast type 2X fiber. So why do our muscles fatigue over time? Well, first of all, let's go through definition of muscle fatigue is the decreased ability to generate force. Several different reasons here. So the first one, we have accumulation of extracellular potassium. And so what that's going to do is that's going to offset the membrane potential so that it's a little bit harder to depolarize the membrane. Also due to a short duration in terms of training and not enough time to generate force. And so, though with time, what happens is that this starts to increase. If we start to deplete our glycogen stores, liver can only hold so much and convert that into glucose to be ready to be used. However, our body doesn't hold glycogen indefinitely. Also, we have a decrease in the sarcoplasmic reticular release of calcium, and so over time this will decrease as we kind of exhaust those transport pumps and then utilize a lot of the ATP for the physical activity rather than for transporting the calcium back into the sarcoplasmic reticulum. Also, we'll start seeing an increase in lactic acid accumulation, and then this will decrease the pH within our muscles, and so this will give us that burning effect, which can be fatal actually for long durations, because then that acidity or those hydrogen ions will circulate through our bloodstream, and then we'll go to areas that are that could be highly damaged, like within the brain. Also, we start to decrease the amount of ATP. We're not replenishing our sources, and rather what we have is a buildup of ADP to offset that, as the ATP is being broken down when it's being used. And then also our motor neurons can be fatigued over time, and so decrease the rate of action potentials that are generated from them. So there are some adaptations that we get with endurance training, and so, for example, helps us with increased ability to use fatty acids as fuel, and helps to increase intracellular triglyceride storage. Also, where there's an increase in lactate threshold, we'll have a decrease in the type 2X and an increase in type 2A muscle fibers, as well as a decrease in insulin sensitivity, and then also increase in number of mitochondria. There are many more variables and factors that can occur. Here in this table, I mean, it does a great job of giving you a good idea of what benefits occur with exercise. Now, some of the benefits of strength training include hypertrophy, and this is where we'll have an increase in size of the muscle. And so this typically happens within those fast twitch muscles, both intermediate and that fast glycolytic. And so these will become thicker and will actually increase the number of actin and myosin. And so we're inserting or making the sarcomeres larger. What can also happen too is that we can get an increase in number of muscle cells, and that's hyperplasia. This is usually seen when you have like a lot of strength, like when you do a lot of weightlifting and strength training, and it happens over time. And so you're actually inserting more sarcomeres, and this is due to the fibers that are going to split, and so they're both increasing in size and will increase in volume. However, this is something you have to continue doing if you want to maintain it, otherwise they do start to decrease in both volume and in number over time. So unfortunately, as we age, we start seeing a decrease in our muscle mass and volume, and this is inevitable, unfortunately. So usually our type 2 fibers are going to have a significant loss, but our type 1 fibers also will have a loss in appearance, but both can be the rate at which their loss occurs, though, can be slowed down either by strength training or by endurance training. Yeah, it is inevitable that there will be some loss. Satellite cells, which are glial cells, typically, like with healthy young individuals, these are responsible to help build up muscles and support the motor neurons. However, with aging, they start to die off, and they also start to produce more myostatin, which is protein that's responsible for basically waste of the muscle. And so this image here, so here's a healthy, normal, say 25-year-old, and then here's one that has, like, say, is a 70-year-old individual. And so this loss that we see with muscle mass is another term that we use, is called sarcopenia for this.